Hello friends, firstly I thanks for your wishes on Teachers Days to me. On this occasion, in this session, we'll study few theorems on uniform continuity. So our first theorem is today's first theorem about uniform continuity. Composition of two uniformly continuous functions is uniformly continuous. We have proved that composition of two continuous functions is continuous. Here we will study now composition of two uniformly continuous functions is continuous. Composition of two uniformly continuous functions is uniformly continuous. So we'll take two uniformly continuous functions. So let f from xd to y row and g from y row to say z sigma, y row to say other matrix by z sigma be uniformly continuous functions. Uniformly continuous functions. What is your aim? G composite f function from xd to z sigma is uniformly continuous. Is uniformly continuous function. That is to show for given epsilon greater than 0, there exists some delta greater than 0 such that G composite f of sigma of G composite f x 1 minus G composite f x2 is less than epsilon whenever d of x1 x2 less than delta for any 2 points x1 x2 belongs to x. This is our aim. Okay. So fix epsilon greater than 0. Now since G from y row to z sigma, G from y row to z sigma is uniformly continuous, therefore for epsilon greater than 0, there exists some eta greater than 0 such that sigma of g of y1, g of y2, g of y1, g of y2 less than, here also comma, g of y1, g of y2 is less than epsilon whenever row of y1, y2 less than eta. y1, y2 belongs to y. Again, f from xd to y row is a uniformly continuous function. Therefore, for eta greater than 0, there exists some delta greater than 0 such that there exists some delta greater than 0 such that rho of fx1 fx2 is less than eta, okay, whenever d of x1 x2 less than delta x1 x2 belongs to x. Now f of x1 f of x2 is equal to y1 f of x2 is equal to y2 belongs to y. Okay. And therefore rho of y1 y2 is less than eta whenever d of x1 x2 less than delta x1 x2 belongs to x. So this is 1, this is now 2, this is 3. So from 1 to 3, from 1 to 3, 1 to 3, for epsilon greater than 0, for epsilon greater than 0, there exists delta greater than 0 such that sigma of g of y1, g of y1 is nothing but f of x1, g of f of x2 is less than epsilon whenever d of x1 x2 less than delta x1 x2 belongs to x. Okay, this is equivalent to sigma of g composite f of x1 by definition of composition of maps. G composite f of x2 is less than epsilon whenever this word. Okay. So this implies G composite f from, okay, xd to z sigma is uniformly continuous. Is uniformly continuous function. Now we'll take next result. Uniformly continuous function maps Cauchy sequence to Cauchy sequence. Maps Cauchy sequence to Cauchy sequence. So next theorem. Let f from metric space xd to y row be uniformly continuous function and xn be Cauchy sequence in x, then f of xn n equal to 1 to infinity is Cauchy sequence in y. So in xd in y row. So prove. Now since f from xd to y row is uniform continuous function, what this implies is, therefore for given epsilon greater than 0, there exists some delta greater than 0 such that rho of fx1 or fy is less than epsilon whenever d of xy is less than delta xy belongs to x. This is 1. So let xn be Cauchy sequence in x. Let xn be Cauchy sequence in xd. Therefore, for this delta greater than 0, there exists some positive integer n naught such that d of xn xm is less than delta when for any nm greater equal n naught. Nm greater equal n naught. Okay. So from 1 and 2, from 1 and 2, rho of f of xn, this must be less than epsilon for any nm greater equal n naught. Okay. Thus, for given epsilon greater than 0, there exists positive integer n naught satisfying 3, means condition of Cauchy theorem. Therefore, f of xn is Cauchy sequence in y row. Is it clear? Now we'll take this theorem without proof. So let xd and y row, let xd be metric space and A be dense subset of x. Let xd be metric space and A be dense subset of x. Dense subset of x. Let y row be complete metric space. Let y row be complete metric space and G from A to Y, F from A to Y be uniformly continuous function, then F can be extended uniquely to, uniquely to uniformly continuous function g from x to y. So we'll prove this theorem with help of this uniformly continuous function maps Cauchy sequence to Cauchy sequence and composition of uniformly continuous function is continuous, and denseness property of E. Now we'll study definition of homeomorphism. Homeomorphism. So let xd and y row be two metric spaces. xd and y row be metric spaces, then bijective function, bijective continuous function, bijective continuous function f from x to y is homeomorphism if homeomorphism if f infers from y to x is continuous. So f must be bijective, it is continuous from xd to y row, and its inverse function, as it is bijective, so inverse function exists from y to x and it should be continuous function. Okay. If there exists homeomorphism, f from xd to y row, then metric spaces xd and y row are said to be homeomorphic metric spaces. If you take the for example, let AB and close interval CD. This is my x, this is y. Be metric spaces with usual metric. D of xy is equal to mod of x minus y. So that your ABU and CDU are homeomorphic metric spaces. Solution: define f from AB to CD as fx is equal to c plus d minus c upon b minus a into x minus a. Okay, x belongs to AB. So if you observe A to B, and this is C to D. This is your AC point and this is your BD point. Now if I put x is equal to A here, this B minus A get cancelled. F of A takes C value. So F maps A to C and F maps B. If I take B here, what is the value of A? F of A minus A gives us 0. So F of A is equal to C. And if I take B here, B minus A will get cancelled, then we will get D. So B's image is D. And then this is the linear equation. This is linear equation of line. So it is nothing but line segment joining AC point to BD. AC to BD. Right. So this is a bijective function. Okay. Then f is bijective function, bijective continuous function, such that f inverse from CD to AB is defined as f inverse x. This will become a plus b minus a upon d minus c into x minus c is continuous. Okay. So how it is bijective continuous? Why this is continuous? You have to explain it. Implies f is homeomorphism. Homeomorphism. And therefore, closed interval AB and closed interval CD are homeomorphic with respect to usual metric space. With respect to usual metric. Next one. Let R and minus pi by 2 be metric spaces with usual metric. With usual metric, usual distance metric. D of xy is equal to mod of x minus y. So that minus pi by 2 and R are homeomorphic. So you have to give some bijective function. Okay. And you are well familiar that tan x is bijective function from minus pi by 2 to RU. Okay. So here f from minus pi by 2 to R defined as fx is equal to tan x is bijective continuous function such that f inverse from R to minus pi by 2 defined as f inverse x is equal to tan inverse x is continuous function. So, why this is bijective? You have to check it. You have to explain it. This implies f is homeomorphism. And therefore, open interval minus pi by 2 and R are homeomorphic metric spaces. Homeomorphic metric spaces with respect to usual metric. Both have usual distance function. So, students, in this lecture, we have studied two important results about uniform continuous functions and we have started homeomorphism. So, with this discussion, we'll stop our today's session here. If you like the video, subscribe channel and like the videos. Thanks.